Welcome back to Astronomy 101. This is the beginning of Chapter 5, Light and Matter. In Chapter 4, you got your beginning introduction to physics, where we looked at motion and gravity and energy. And in Chapter 5, this will continue your introduction to physics and also give you an introduction to chemistry. So the chapter title is Light and Matter, and we're going to look at how we use light, how we interpret light from the heavens, and figure out what is out there in space. So the subtitle of the chapter is Reading Messages from the Cosmos. I've divided this chapter up into many videos, I think 8 in total, to keep each one little bite-sized chunks. And so we'll start with part 1, Light in Everyday Life. We measure the flow of energy, which is called power, in light in units of watts. And so you think about like a 100-watt light bulb. The watts refers to how much energy in a given amount of time comes out of it. So 1 watt is defined as a joule per second. A joule is a unit of energy, and seconds, of course, is time. So 1 watt is a joule per second, that's in metric units, but we can also measure power in calories per hour or calories per minute. So you think about on a treadmill, oftentimes, it gives you your rate of power, tells you what intensity of exercise you're doing it. So it gives you that to you in either calories per hour or calories per minute. We also measure with automobiles power in horsepower, and 1 horsepower is defined as 746 watts. In this class, we won't be using calories per hour, calories per minute, or horsepowers, but we will stick to watts. Let's now talk about the colors of light, the rainbow of light, and I want you to notice in this picture that a rainbow is a continuum of light. So there aren't these discrete colors, like if you were making a rainbow out of maybe crayons or markers, you maybe make a red stripe and then an orange stripe and then a yellow, but rather it's a continuum. It's red blending into orange, which blends into yellow, which blends into green. And let's zoom in on this picture. And so a small part of that picture, you can see there's red, then what we might call red, orange, orange, yellow, yellowish green, and on into green. So colors, which are actually frequencies of light, which I'll talk about in a bit, they actually come in a continuum. Here's a rainbow, and you notice that with a rainbow, with a spectrum of light, they're always in the same order. Now, we typically learn those as 7 different colors, sometimes 6, but the 7 we traditionally learn: red, orange, yellow, green, blue, indigo, violet. Sometimes indigo and violet are replaced with just purple, but we'll stick with the 7 colors in this class. So red, orange, yellow, green, blue, indigo, violet. Those are always in a certain order, and they go in frequency, which I'll explain in just a little bit. So red is the lowest frequency of light, and then orange, then yellow, all the way up to violet being the highest frequency. And here they are, these letters down here, they spell Roy G. Biv, so very easy to remember if you just think Roy G. Biv. Now, a rainbow doesn't have to be up in the sky with rain. You can have a rainbow when there are sprinklers going on in the yard. So as long as the sun is behind you and you have water droplets in the air, you can possibly get a rainbow like this. What's happening in a rainbow is that the sunlight coming from behind you is getting reflected. It actually goes into the raindrops, or the water droplets. Now, most of the water droplets actually go straight through. However, some of them actually reflect internally in the water droplets and then come back out to your eyes. And the different colors, the different frequencies reflect at slightly different angles. Isaac Newton, among his many other discoveries and contributions to science, he discovered that white light is made up of all the colors of the rainbow. So here is something reminiscent of Newton's experiment. He took white light, and this looks like it's from a flashlight, but it could also be from the sun, and sent it through a glass prism. And when it goes through the glass prism and it reflects internally through it, all the different frequencies, they reflect at slightly different angles. And so you can see the different colors broken up, and we call that the spectrum of light. Now we're going to look at the different ways that light and matter interact. And this is very important for our study of astronomy. In fact, all of Chapter 5 is very important, laying that groundwork for understanding astronomy. Throughout the semester, I'll be teaching about planets, nebulae, comets, galaxies, and all these things that are out there. And you have to understand that pretty much everything that we know about those things that are up there in the sky, we only know because of the light that we receive that came from it. So we need to be able to interpret what that light is telling us about the objects out there so we can learn about those objects. So we're first going to talk about how light and matter interact. And there are four basic ways. They are emission, absorption, transmission, and reflection, which subcategory of reflection is scattering. So let's talk about each of those. Emission, the idea here is that matter can emit light. That doesn't mean that all matter will emit light, but it can emit light. And so examples of this are light bulbs and stars. What you see here, we have some Christmas lights around the house. We have neon lights, and what you'll see later is that even though we call them neon lights, implying that there's the element neon in them, only the red ones are neon. So blue, yellow, orange, those are created by different elements, which we'll get into later in this chapter. We have the star, like our sun. And here's a globular cluster of about 1 million stars together. Notice the different colors. But all of these are examples of emission of light. And what that means is that the matter actually gives off light. It generates, it creates light, and gives it off. Next is absorption. And when you think about absorption, a good example is a black surface. And so the idea here is that light is absorbed by dark surfaces. The light is absorbed, but remember, energy is not destroyed. Something happens to that energy. So often with dark surfaces, the dark surface, like this black clothing, will absorb the light and actually turn it into heat. And so this is why many people don't like wearing dark clothing or black clothing during the summer, just because it's hotter. It's lighter clothing, like white clothes, light colors that tend to reflect light more and not absorb it and turn it into heat. The next way that light and matter can interact is by transmission. Transmission means that light actually goes through the matter. So emission, so far what we've covered, is light giving off, or matter giving off light. Absorption is the opposite of emission, where the light falls on the matter and it gets absorbed. Transmission is where the light just goes through the matter, like with these windows. Now there are different kinds of transmission. We can have transparent windows, which means the light goes through and we can see details. We can see images on the other side. There's translucent objects like this stained glass window, and this is where light comes through, but you can't see details of the things that are on the other side. But in both cases, between transparent and translucent, the light, to some extent or another, actually goes through. And the opposite of these is opaque, like a brick wall, where light just does not go through at all. The fourth way that light and matter can interact is called reflection. And a subcategory of reflection is scattering, which I'll get to in a bit. Now reflection, I want you to think about a mirror. Light reflects off of a mirror, but actually, if you look around the room that you're in, pretty much everything you can see, you see it because light is reflecting off of it. Now I said pretty much everything. You're looking at a computer screen, and so that screen is emitting light. And if if you have any light bulbs in the room, they are emitting light. But other than that, the things that you see around you that are not emitting light, they are reflecting light into your eyes. Now, there's a little bit of geometry to it, very simple geometry. It's like a ball bouncing off the wall. So if it comes in at a 50-degree angle, it's going to bounce off and go off at a 50-degree angle. So that's what's called reflection. Now, a subcategory of reflection is what's called scattering. And this is at the very small level, the molecular level. When you have air molecules, it doesn't have to be air molecules, but I'm just using those as an example, many molecules, and light goes through them. Individually, each molecule can reflect light. So each one acts like a little mirror. It's an interesting question. Why is the sky blue? And scattering is the answer. So what happens, here we have this light blue area is Earth's atmosphere. Think of that as the sky. We have sunlight coming down from space, and there's the whole rainbow, Roy G. Biv, all the colors of the rainbow that are wrapped up in white light. And as it goes through the atmosphere tends to scatter the higher frequencies, so the blue and the violet. It scatters in all directions. And so notice all going in random directions because the light will hit each molecule at a slightly different angle, and there are trillions upon trillions of these molecules. They'll all go off at different directions. And so if you're standing right where my marker is, you will get a whole lot of blue and violet. Now our eyes are more sensitive to blue than to violet, and so we will see blue. And if you're standing over here, pretty much any random place I put my marker, if you're standing there, you're going to get blue light coming into your eyes. Also, notice what happened to the direct beam of sunlight. The blue and the violet got scattered out. And so what we're left with is the lower frequencies of light, red, orange, yellow, and green. And so somebody right here will tend to see not so much white light, but more yellowish light. And the more atmosphere that sunlight has come through, the more reddish, the more orangish it's going to be. Now, when the sun or anything in the sky is low on the horizon, sunrise and sunset or moonrise or moonset, that's when the light is traveling through the most atmosphere, the most air to get to us. So it's going to have a very reddish or orange color. And so here is the sunlight. The sun is at sunset or maybe sunrise, and the light goes through and the blues and the violets get stripped away, and all that's left is the lower frequencies, which tends to be more reddish and orange. And so you will see a red or an orange sunset. You can see this with the moon. It's most noticeable to people when it's a full moon, but really any phase of the moon. When the moon is low on the horizon, it's got an orangey yellow look. But give it a few hours, it gets higher in the sky, and then it looks white. And the reason is when it was low on the horizon, the higher frequencies got scattered out, and you're left with the lower frequencies, the red, the orange, and the yellow. This is also the explanation for why a lunar eclipse looks red. Remember what a lunar eclipse is. You've got the sun, you've got the earth, and you've got the moon. And the earth blocks most of the sunlight. But the little bit of sunlight that gets to the moon is the little bit, trace my line here with the marker, that is skimmed through Earth's atmosphere. And it's become red and skimmed through Earth's atmosphere on all around the Earth. It just skims through. And so the light that the moon is getting during a lunar eclipse is only the light from sunsets all around the world. And so it's only red-orange light. It hits the moon, and then it reflects back to Earth. So we see a dim red moon on a lunar eclipse. So there's a nice red-orange lunar eclipse. Let's look at these diagrams right here. If you have a white surface, what does it mean to be a white surface? Well, that means that when white light hits it, it reflects all of the wavelengths. So white light, which remember is really a combination of red, orange, yellow, green, blue, indigo, and violet, it hits the surface, and all those wavelengths, all those lights, those colors, they bounce off. So a white surface is white because it reflects all the wavelengths. Now, if you take a white surface, maybe a white shirt or a white piece of paper, and you put it in a room where there is only a red light, if you have a red light bulb, it will look red because while it is able to reflect all of the wavelengths, it's not going to reflect wavelengths that it's not receiving. And so if you shine a red light on it, it will reflect the red. If you shine a blue light on it, it will reflect the blue. But we're talking about normal light, like from light bulbs or the sunlight, which is typically white, and so it looks white. Now, if you have a black surface, remember a black surface is a good example of absorption of light. You hit it with any wavelength and it will not reflect the light. Now, a perfectly black surface does not reflect anything. However, there's different shades of that. So you can have a shiny black surface, which means basically it does a very good job of absorbing wavelengths, but some it does reflect off. And now let's take a red surface. A red surface is one that if white light hits it, it will only reflect off red. It will absorb the others. So here we're looking at a combination of absorption and reflection. It will only reflect red, and a green surface will only reflect green. So let's take a look at this plant that's glowing, that's growing rather. It's got green leaves, it's got red flowers on it. The sunlight, which is white light, but remember, white is a combination of all the colors, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. They're all hitting the plant. But the green leaves are green because they absorb those wavelengths and they reflect off green into our eyes, and we see green leaves. The red flowers absorb all the wavelengths except red. They reflect red into our eyes, so we see red. This is a picture from the book. Just many more examples. Here's the white sunlight. The sun and the lamp, they both emit light. So this diagram here is just a review of all the different interactions of light with matter. A mirror reflects all the colors of visible light. Let's see, the chair is red because it scatters red light. You can just say it reflects it, but scattering works as well. But it absorbs all the other colors. The snow absorbs sunlight, some light, which aids the melting. So again, that's the light being turned into thermal energy, but it scatters most of the light, so it looks bright. And again, the difference between scattering and reflecting. Scattering more refers to when it goes at many, many different angles. The glass transmits all colors of visible light. And here we have the tree, which absorbs most of the colors but reflects off green. So interactions between light and matter determine the appearance of everything around us. What have we learned so far? How do we experience light? Light is a form of energy. It is that third category of energy that I alluded to in chapter 4. Remember in chapter 4 I said there are three categories of energy: kinetic, potential, and radiative. So light is radiative energy because it radiates outward. Light comes in many colors that combine to form white light. How do light and matter interact? Matter can emit light, absorb light, transmit light, and reflect or scatter light. Interactions between light and matter determine the appearance of everything we see. And that's it for part 1 of chapter 5. Have a great day.